capture to work, please go ahead and join me. Okay. All right, folks. So I have given you elementary steps. What does elementary steps mean? By the way, did anybody have any of this information in Gen Chem 2? Ever hear of elementary steps? Molecularity? No? Okay. Anyways, if you remember your rate stuff from Gen Chem 2 at all, molecularity is actually where you get your orders for your rates. That's actually where that comes from. And molecularity comes from the elementary steps, specifically the slow step. Okay. That is the same information we've been doing so far. Now, having said that, I've given you elementary steps that are very common in organic chemistry. Now we're going to be assembling those elementary steps into mechanisms, which are going to be multi-step. You've already done this a little bit, and I've seen you've seen a little bit of this where we did like two-step mechanisms, right? Okay. By the way, when I learned this, we would do a full mechanism exam. Each of the mechanisms would be a page long, and we do 6 pages of that. Every week. So, yes, I am. I know that it seems like I'm awful, but I'm not that awful. Okay. So here's the mechanism for the general SN2 reaction. Again, remember that is the nucleophilic substitution. That's bimolecular. Two things are coming together at once. Notice that terminology and naming is fitting exactly with what you covered in, well, it should have covered, if you did not, in General Chemistry 2. Remember the orders, bimolecular, two things coming together? Okay, kind of. All right. So unimolecular means one thing coming together, right? Okay, bimolecular, two things coming together. Is there a 3 things coming together? Trimolecular would be the name. Does that actually exist, though? No. 2 things coming together is already hard enough to happen, right? 3 things all coming together at once is basically almost impossible. Okay? It's just so low a probability that almost never happens. And so it's unlikely that any significant mechanisms ever will exist for it. But every now and then somebody says, I discovered it. And then somebody actually does the experiment and goes, nope, that was wrong. It's 2 steps. But maybe one day. Maybe. Okay, so again, SN2, bimolecular, everybody's comfortable with this. Everybody remembers that. I was actually pleasantly surprised. People did pretty decent on the mechanism stuff. Okay, and again, we have our nucleophile. It is attacking our substrate or electrophile, right? And it is donating electron density into it. We then have the leaving group leave with the electrons. Okay. Anybody have any questions about that so far? Okay. All right, so let's talk about the mechanism for an SN1 reaction. Now, an SN1 reaction we hadn't really gone into yet because we did not do multi-step reactions, did we? And an SN1 mechanism has to be multi-step. That's because the initial slow step is going to involve a single species. Okay? And that is going to be, the leaving group is going to leave with its electrons, leaving behind the carbocation. Can everybody see that step okay? That's a very high energy step, isn't it? Yeah, we're generating carbocation. So what's going to happen next is this leaving group is going to drift off. We are then going to have the nucleophile. That nucleophile will attack the carbocation. Now, notice, does this nucleophile actually have to be any good as a nucleophile? No, we're starting as a carbocation, aren't we? That'd be like saying, do we need a really good axe if we throw dynamite at a tree? No, not really, right? We just need something to fulfill the last pieces, right? So In these cases of an SN1 reaction, this nucleophile does not have to be very good. It's going to be attacking a carbocation that's already positively charged, already easy to make a bond with. So the next step that's going to happen here is, again, we donate the electron density into that carbocation. This is going to be step 2, where it makes the bond with the nucleophile. Notice, again, we did the same substitution. It just took 2 steps, didn't it? Everybody see that okay? Okay, so this is a 2-step mechanism. Why is the molecularity 1, by the way? Why is it an SN1? Eventually, 2 things have to come together, right? It's the slow step. The slow step is always what we talk about. Okay? So I drove from Green Hills today. Am I going to be like, that drive took so long, it took forever, I had to start my vehicle? Did that make any sense? No. Why would the drive from Green Hills be long? Traffic. Yeah, I had to get on the main road and traffic, 2 school zones, blah, 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 right? And it's the slow stuff that's going to be the stuff that would be concerning me, right? Same thing with a reaction. So this right here is the slow step because we have to actually have the leaving group leave, right? It's not going to want to leave, is it? Okay? It's going to sit there and it's going to stretch that bond out and then spring back most of the time. Okay? And every now and then, it's going to pop off. Right? And that is going to be our rate determining step. That's what makes this a 1, unimolecular, okay? The other one, where we had the SN2 reaction, this is our rate determining step. This is the slow step. We have to have that nucleophile attack, and then the leaving group pop off from that attack, right?
So you know how it takes energy for the leaving group to leave?
Mm-hmm.
If there was more energy, would it increase the reaction, making it faster?
It would.
So that would change the type of reaction?
It's unlikely you're going to be able to make it energetic enough to overcome a carbocation.
Okay.
But yes. Yes. What would happen is you'd actually start shifting towards an SN2 mechanism. Yeah. And that's actually what will happen, actually. You can get like this nucleophile, really, really good nucleophile here. And then this can be something that's drawing a ton of electron density from that carbon. And you can make it faster and more energetically favorable to do the SN2 instead. And then you'd get either no SN1 reaction or a little bit of SN1, and then SN2 mostly. And you can do vice versa. You can give a really crappy nucleophile that doesn't do a very good job attacking, and then you can end up with an SN1 reaction instead, because the nucleophile just sits there and doesn't attack, and so eventually the leaving group leaves and you get an SN1, right? Yeah. And that same thing will also happen with the eliminations as well later. Okay, but we'll build up into it. Yeah, but you made a good connection. Okay, folks. So again, this is the overall reactants, overall products down here. So this would be the overall results of that SN1 reaction. These right here would be the elementary steps that would give us the mechanism for that reaction, okay? And so the overall is like saying, I took a trip to Vietnam, okay? Well, you know the overall gist, right? I went to Vietnam, I came back, okay? But you don't know any of the steps in between, do you? Like, you don't know I laid over for 2 days in a Japanese airport as 9 million COVID cases went through. Because China opened its borders when I was flying back. Which is true. That was pretty brutal. I'll tell you what, the Japanese airports have hotels next to them. Now that's what you're supposed to use, but they didn't allow us to leave the airport. So the Japanese airports have absolutely no places to actually sit there comfortable. Yeah, because they're not meant to be used that way. Brutal. Anyways, so notice that, what are we saying about this carbocation? Why isn't that showing up in this overall reaction? Where's my carbocation? Where is it? Yeah, they cancel, right? When we look at reaction, they are equations, aren't they? If we have a minus 1x on one side and a minus 1x on the other side, what do? We cancel them off, don't we? Okay? Same thing happens here. So we are canceling our carbocations here. Again, those are our intermediates. Everybody's comfortable with intermediates? What's different between an intermediate and a transition state, by the way? Okay, so this right here is your reactants. And when we do a reaction, we have to overcome the high energy state, which is the transition state, right? And they're going to be peaks. They're the high energy states you have to overcome, okay? And then an intermediate will actually be a lower energy valley between transition states. It's something that will exist for a short period of time, typically in situ. Do you know what in situ means? In solution. Anybody know what in vivo means? In living organism, yeah. In your organism you're talking about, right? So in situ, in solution, you are typically not going to be able to obtain intermediates and purify them, okay? There's stuff that you have to generate in place, and then they get used up right away. But very different than a transition state because they do have some degree of stability, okay? They will actually exist for some reasonable period of time. It might be up to even seconds. Okay, and so the transition state is actually that carbocation right there. Okay, and then we're going to have to overcome another transition state right here from this intermediate carbocation, excuse me, and that's going to go to our products. This is what makes it two-step, by the way. Can you see that? Step 1, step 2, right? Okay. Literally, we are stepping over the hills. All right. So this right here is a bimolecular elimination. I had hinted at it before, and you can kind of start seeing that connection if you want. But
So is an SN1 just like splitting up on SN2 into the different sets that it has, or
kind of in reordering.
reordering?
Yeah. So in an SN2, we have the whole thing happen in one go, and this transition state is usually very high. Okay. So it'd just be one step. That's it. Okay. And SN1, on the other hand, we have to have the leaving group leave first. Then we get the carbocation. That gets attacked then. Okay. And so it does split it up into two steps, but it does end up creating this high energy intermediate. So, and a lot of this depends on the height of the hill here versus the height of this intermediate, which one's higher, of which one would happen. Does that kind of make sense?
Yeah.
Yeah, it's a bit like splitting them up and then rearranging it. Yeah. Because typically an SN2 is going to be initiated by the attacking nucleophile. Okay, so let's go ahead and look at the mechanism for a bimolecular elimination.
Sorry, just to clarify.
Oh, no.
Before you move on.
Yeah.
So you're saying for SN2 reactions, the nucleophile attacking the substrate is what pushes the reaction forward, whereas the SN1 reaction, it's the leaving group
Yes.
that allows the nucleophile to attack.
Okay, so this is a more useful picture in your head, and this is going to become more obvious the way I'm doing it, where I'm talking about how the nucleophile attacks, and that causes the SN2. And the reason for that is the nucleophile being a better attacker is actually what's going to determine whether you have an SN2 or not.
Gotcha.
Yeah, but realistically speaking, an SN2 happens all at once.
Okay.
Yeah. So literally what happens in an SN2 is the nucleophile and the leaving group both end up bonded. And then if it falls apart with the leaving group leaving, you get to prongs. If it falls apart the other way, you just go back to reactants. Yeah. Does that?
Yeah, that makes sense.
Yeah. It's not technically correct to say that it's initiated either way, because the leaving group is already pulling its electron density away before you ever attack.
Okay.
Yeah.
I got you.
But the way I'm saying it is much more useful for outcomes, like which one happens, sort of stuff. Did that make sense?
Yeah.
Okay.
I appreciate it.
Hopefully I didn't overly complicate that.
No, you're good.
Yeah. I didn't want to lie to you and tell you something that's not quite right, but yeah.
Okay.
Yeah, it does make it more complicated to actually be fully understand it, right? Yeah. An interesting factoid, I'll just let this be out there for you for if you go on to biochemistry or something like that. Enzymes oftentimes do this trick. We have big barrier, we split it up into multiple steps, which gives us smaller barriers overall. Okay? And so enzymes oftentimes do things where it's SN2. Normally, if we did it organic chemistry lab, now it's SN1 in in the biological systems enzymes. Okay, so the mechanism for your general E2 reaction is going to look like this. Right here, we're going to have a base. What's the difference between a base and a nucleophile, excuse me, by the way? Man, I need to start bringing cold water to this place. My throat gets really...
It doesn't help.
Doesn't help? Man. Actually, I'll bring an extra fan next time as well. Hopefully that'll help a little. Okay, so what's the big difference between a base and a nucleophile? So a nucleophile donates electrons, right? A base donates electrons. A base does it to protons, yeah, but electrophiles can do it to protons. What's the big difference? Yeah, so most nucleophiles are bases as well. Okay, overall, most bases are nucleophiles to some degree. Most nucleophiles are bases to some degree. Okay, the big difference between them is nucleophiles have orbitals that can come out and reach and attack those positively charged carbons. Okay, and so it doesn't need to just accept a proton onto it. A base, on the other hand, is not as usually good at reaching out and attacking those carbons. Okay? And so it's more easily to accept that proton onto it. Is that making some sense? Okay. So keep in mind that all these mechanisms I'm talking about, they're all going to get interrelated. You could have all of them happening in one mixture. Okay? Okay, so our base is going to attack this hydrogen here. This hydrogen here is going to be the next one over, that alpha carbon. Why is it always the alpha carbon, by the way? Remember, this is our nucleophile, right? That positively charged carbon right there. Why is it that next one over? Yeah, that leaving group has been pulling electron density away from that carbon, right? And that carbon's pulling the electron density away from this hydrogen, isn't it? Yeah, these bonds are already partially overlapped, and those electrons are already getting pulled over onto that carbon. Does that make sense? So this arrow right here had always existed to a little bit. It just hadn't gotten finished, right? It hadn't actually been pulled over. Okay? Okay, so the base is going to give its electrons into a bond with the hydrogen. This is then going to cause the hydrogen's electrons to get pulled into a bond between those two carbons. This will end up making a double bond. This will allow the leaving group to pull the electron density that was in the sigma bond here over onto the leaving group and leave. Everybody okay with that so far? Okay, fantastic. This gives us the conjugate acid, the leaving group, which is now a conjugate base. Everybody see that okay? And our double bond right here. Okay. All right, let's talk about the E1. So the E2, again, we have an attack happening, don't we? And that allows this reaction to occur. One step, just like the SN2 and everything like that, right? Okay, the E1, on the other hand, is going to be where the leaving group leaves first again. Okay? Very like the SN1, right? They're very related. So that leaving group here is good enough that it can leave with the electron density, leaving behind the carbocation. Once the carbocation is left, this is going to start pulling this electron density over from this hydrogen a lot, right? This is hydrogen is going to become very, very acidic. Now, whenever you have carbocations, remember those rearrangements we talked about, where we had the hydride shift, methyl shifts? Those are always possible whenever we have carbocations. But that also helps you understand why this hydrogen becomes so acidic, right? Because the electron density is getting pulled over onto the carbocation by that orbital overlap that we talked about before. So now we have a very acidic hydrogen here. Our base can then donate its electron density into a bond with the hydrogen. It will pull that hydrogen away, leaving the electron density to form a double bond with that carbocation. That will give us the double bond, again the conjugate acid here, and notice our leaving group skedaddled before. Okay? Our leaving group left before. Right, again, this is the bimolecular, this is the E1, where we have it in 2 steps occurring, okay? All right, anybody have any questions about that one so far? Okay, very good. And again, what would determine which one of those would happen, by the way?
How much energy?
Strength of your base is going to help determine that. There's one more thing. Well, ultimately, yeah, it would boil down to transition state, but what determines those transition states? How about how good of a leaving group the leaving group is? Yeah, that's going to be a big factor here, right?
Is a better leaving group just more electronegative?
A better leaving group is more electronegative, but also can hold on to that electron density and be more stable. So this was very stable as that negatively charged leaving group. And that's why you get things like fluoride isn't a particularly great leaving group, because the electron density around it is just too concentrated. It's too small.
So bigger.
Yeah, bigger usually helps. Resonance states that it can form and distribute the electron density around it helps a lot too. Okay, so this right here is the overall reaction for an E1 mechanism. And everybody's okay with that, right? So if we added all the parts together, that's what we get. Notice again, we end up dropping the carbocations, right? Because those are intermediates. So this right here is your free energy diagram. And just like you had mentioned, again, the transition state is going to end up determining this. Okay? But we had been talking about why the transition states are like they are. So again, here's our reactants. We're going to overcome the first transition state. And in this case, that transition state is when that leaving group starts breaking that bond, but it's just a very extended bond. Okay? And what's going to then happen is it breaks that bond, and we're left in this state, which is the intermediate right here. You can think of this as the rearrangement of those orbitals, because we went from hybrid orbitals to a p orbital, right? Yeah. Okay, and this then is going to overcome the second transition state for step 2, and it will finally go to products here. Everybody okay with that so far? Okay, very good. Okay. So, some of the most important evidence supporting the different mechanisms that's proposed for the SN1 and SN2 nucleophilic substitution reactions. as well as for the E1 and E2 reactions, is going to come from your kinetics. How fast things happen when we change conditions. Okay? So your rate laws are going to correspond to the differences in their respective free energy diagrams. And this is how we actually figure these things out. Okay? So like, which mechanism is this random reaction I just invented? Okay? Do you remember doing an order, figuring out orders for rate laws back in Gen Chem 2? You probably did a lab involving it. Yeah? Yeah, you always take experimental data and you figure out the orders from those. That's what we do. Okay? If you're trying to figure out a mechanism, that's how you figure out what are valid elementary steps. Okay? All right. And so, for example, this right here is an SN2 rate. An SN2 rate will have a rate constant. That's this K here, small k. Anybody know the difference between large Ks and small Ks? So large Ks are equilibrium constants, right? Small Ks are rate constants, okay? And the big difference is actually when you have a large K, it's actually a sum of small Ks. It's small k divided by small k. Sometimes there's some multiplications involved, okay? So that's actually the difference, because when you have an equilibrium constant, you have two reactions that are going equal rates in both directions, right? Okay, so this right here is the SN1 rate. So this is going to be our rate constant. And notice we only have one species here. Why do we only have one species? This one has two. Yeah, that's the one, right? That's why it's SN1, right? It's unimolecular. The slow step only has one species that the concentration matters for. Okay? On an SN2 reaction, it's bimolecular because we need both of those to come together on our slow step, right? Okay. Okay. So on our E2, guess what we're going to have? Two species, right? We have to have our base. We have more base, more concentration of base. We're going to get faster reaction, right? We have more concentration of our substrate. We're going to get a faster reaction because we need those two to collide to get a reaction going. If we go to an E1, though, does our slow step depend on anything colliding with anything? No, it doesn't. It just depends on how much of that substrate we have. How often is that leaving group going to leave, right? That's all that matters. And so those are the rate laws. Okay, let's go ahead and do some comparisons. So these are the rates of the SN1 and SN2. Notice they differ in the way they depend on the reactant concentrations. They both have the substrate, but in the case of the SN2, we also need the nucleophile, right? So the nucleophile actually takes part in how fast this reaction is going to happen. Okay? On the other hand, for the SN1 reaction, it essentially does not matter how much nucleophile you have. You just have to have the nucleophile in enough concentration the reaction can actually still go forward. Okay? That the number isn't something near zero. All right. E1 and E2 reactions are going to differ in their rate laws as well, of course. And again, it's the substrate, same. It's going to depend on the concentration of the substrate for both of them. But for the E2 rate, it's going to depend on how much base you have as well. Okay? More base means more collisions, means more reaction, right? Okay, so rate determining step of the mechanism. This is called the slow step of the mechanism. This is going to be the elementary step that dictates the rate of the overall reaction. If the species appears in reactant in the rate determining step of the mechanism, then the overall reaction rate is going to depend on the concentration of that species. I got 2 minutes, don't I? So this is actually a pretty good mental picture, but I'd already kind of used something very similar to it, didn't I? Okay. So again, this is like the slow lane versus a fast lane. How long you have to stay in the slow lane is really going to determine the length of your trip, right? popping into the fast lane is not going to really determine the length of your trip, because that's going to be so much less time you spend there, right? Okay. Okay. All right, so let's go ahead and end on here, actually. This is actually a pretty decent place to end. Yeah. Okay, and we will start here next time. You all have a wonderful day and week, I guess. I'll see y'all on Friday, hopefully, for lab.